So the average on this one was a little lower than I was expecting. One of the problems, or a couple of the problems, turned out to be fairly difficult for people in terms of mechanisms, so we can go over that today. The key is already up and posted, so you can check your stuff against that if you want to submit a regrade and feel like you might be deserving of more points back. As always, the procedure for submitting regrades is staple a sheet of paper on the front of the exam. Please do it on the front because of my whole organizational system based on flipping the page back and forth depending on which problem I'm grading. Do it on the front, stick it into my mailbox or bring it to my office or hand it to me before or after lecture sometime in the next week. And then I will go through that stack once the deadline passes and let you guys know whether I feel it was graded unfairly versus the key. And then Sapling Chapter 22 is due 9 a.m. Friday. Okay, so I guess this is a good time for a pep talk for anyone who's upset about how they did. So please bear in mind that there is a curve of 11.5 points. So whatever you got on the front page, add 11.5 to it, and that's the score that I put online. And the standard deviation was pretty wide. Like this one, people were all over the map, which is kind of usually how it goes throughout the semester of OChem. People start out much more closely spaced, and then things kind of diverge over the course of the semester. Max 107, holy crap, good job. Min 3, we should talk, but yeah. But I guess as a reminder, I do still have that final exam grade replacement policy. So as long as you've been trying the work consistently, it is still possible to do, really well on the final and have that grade replace your entire course grade. Just, if whatever you're doing study-wise is not working for you as well as you would like, this is the time to try switching it up a little. So if you're not already doing these things, like working more practice problems, like the recommended textbook problems, going to help room if you get stuck, meeting up with friends who are in the same class to study together or exchange tips, maybe hiring a tutor if you can. All of these are things that if you're not doing them already, maybe give them a try and see if that turns out to be the thing that you need to succeed. Okay. Any questions about any of that? Okay, cool. So I think I'll more or less go through this in order, but I might not do all of every problem. I guess for problem number 1, how many people want to see the answer to A? Okay, at least one. All right, let me actually go through all the letters and then we'll see which ones have the most support. Okay, how about B? No? Okay. How about C? Okay, D? Okay, a lot of people on D. Okay, so I might skip to D. Because 1,3-butadiene is a diene. I'm hearing a lot of people just go, so yeah, this is Diels-Alder actually. This is a flashback from a couple exams ago. But because this one, it does conjugate addition real well, like it did in parts A through C, or 1,2 versus 1,4 addition. And it also is a great dienophile for Diels-Alder. So I actually stole this directly from the end of the textbook chapter problems that were recommended in the syllabus. So it's not actually drawn out this way in the chapter, it's just like the names of the compounds, but I totally stole it out of there. So working the textbook recommended problems, sometimes very beneficial. All right, so pretty much we're just going to get this is the product. Okay. How about E? Okay, I'll do E. All right, so E, same starting material. And ETS Na. Hopefully you got to the point of being able to split this into 2 ions. So this particular one, pretty much all of the nucleophiles that we saw in the 1,2 versus 1,4 addition section assume that it adds 1,4 unless we know specifically that it does 1,2 or a mixture. So there's a very short list for 1,2 and a short list for mixture. This one happens to be on the 1,4 list. So any kind of RS minus is going to be in this category. So we do, and you didn't have to show the mechanism, but if you're wondering what happens, so we do 1,4 addition onto here, kick that up. This one I actually got kind of sloppy in how I wrote it. So there should actually be two valid ways to write the answer. If you wrote the negative charged version, you should still have gotten full points because technically I did not include anything protic in this.
Is there a reason that it can't deprotonate individually and then you would
Yeah, the pKa of this is way lower, like sub 10 or so, and so it's just not strong enough. Plus, oh yeah, I guess it could if it were a stronger base, it could do it out here. So yeah. Okay. So technically, if you showed it as this, it should have been marked correct, because my bad, I'm not including a protic source. If you were including protons, or assuming that protons were around, maybe if I had written like the conjugate acid of that, then you could have finished this one up as this product instead, the 1,4 addition product. Okay, so either of those should have been marked okay. Questions about that? Okay, cool. How about F? No? Okay, F? All right. Okay. Okay, so this one we got H3O plus in heat. The ester is first of all going to hydrolyze under these conditions. So hydrolyze the ester first, and that gets us to carboxylic acid. And now this is looking like something that could do a decarboxylation and drop its CO2 off. So that goes away. And you end up with just an H there. And if you wanted to, you could also show CO2, but we didn't require it. Okay, questions about that one? Okay, cool. How about G? No? Okay, how about H? Okay. How about I? Okay, and then...
I have a question on H.
Uh-huh.
Shouldn't there have been like a pyridine or something to soak up the HCl?
So I guess the MEOH is also like not a great sacrificial base, but it can also do the job.
Okay.
Yeah, so if you assume two equivalents of MEOH, it still works okay, which we assume it's excess, yeah. Yeah, I guess if you were doing this in the lab, you probably wouldn't bother like wasting money on pyridine. You just throw in a whole bunch of methanol. Yeah. Okay. All right, so let's do I. Okay, so so I and J together as a pair, kind of the big thing here is remembering that acidic conditions favor one particular type of outcome in this reaction, basic conditions favor another. So the whole deal with acidic is you make the enol, you attack bromine, you get to here, and then the reaction slows down enough because the first bromine is preventing or dramatically slowing down the addition of any subsequent bromines, that this is likely to be the major product. So just a single bromine addition or halogen addition in acid. By contrast, if we do it in base, then we're going through the enolates, not the enol. So we're going to just halogenate that thing until we run out of room. So I'm going to stick 3 bromines on there. And this is where we get to that weird thing where we've accidentally made a leaving group out of this carbon. And so at this point, another OH minus can come in and do basically acyl substitution, so like kick up, kick down, boot out this whole thing as a leaving group. And you get temporarily to here, which then is just going to do a proton transfer and get you to this carboxylate and then bromoform as a side product. Okay. I think if you left this as the acid, you probably got most of the points. I don't have any notes about how that was graded, though, if you showed it in the wrong protonation state. Okay. Other questions about that one? Okay, cool. So let's move on to number 2 here. Okay, so this is just show how you would make each of these using some kind of enolate chemistry. Okay, so if you remember that oxidation states trick that I covered on Monday, that actually makes these problems a fair bit easier. If you've got 2 carbons, one's in a lower oxidation state than the other, probably the one that's lower is the carbon that got attacked. So you want to draw the disconnect right next to them. So that means that we would have come into this from this aldehyde where it's oxidized up by 1 from how it is in the final product, plus also this aldehyde. So this one turns out to be 2 copies of the same aldehyde. Mm-hmm.
Just a question. Due to the conjugation, was this? I thought this would go straight to condensation potentially. Like, I mean, it's like the only way you can set it up, but I was curious.
Yeah.
If that's a consideration.
So I guess, yeah, I didn't go into too much details about conjugation favoring aromaticity. You're right that this is a bit dicey in terms of actually getting the product that we want. If you cool it way down, you can disfavor elimination enough that it might make that one. But yeah, I sort of swapped out the R groups from something that I had previously and didn't think about checking for conjugation, so good catch. Yeah. Okay. So 2 copies of the same aldehyde, and then we don't need any particular fancy bases. If you'd written LDA here, that works fine. Or you can just use pretty much any base, like OH minus, or like ETO minus. Pretty much any of those is going to work great for this. Okay, no heat though. All right, questions about that one? Okay. Okay. Okay, so this one, we don't actually have 2 different oxygens anymore. Oh, question, yeah.
Sorry, on the last one, with this solvent, is ethanol, would that not work?
So ethanol in combination with probably its conjugate base would work. And the same for hydroxide in conjugation with its conjugate base. Yeah. Yeah, nice. Yeah, so I guess like just the solvent by itself wouldn't do much. Okay. So for part B here, we don't have 2 oxygens, so this is looking like a condensation product. And for those, the cut line is just across the double bond. So we need that plus that. Okay. So again, if you want, you can use LDA very precisely, deprotonate over here, and then go attack here, and then since we are driving for the conjugation product here, we are going to have to do like a protonation step and then heat it to force conjugation. Or we can just, so is there any other alpha hydrogen on this whole combination other than the ones that I want to pull off? Right, yeah, so pretty much if I throw this in with whatever regular base, it's still going to do pretty much what I want. So just like OH minus, H2O and heat would also be fine. Or ETO minus and ETOH and heat. Uh-huh.
So if there was an alpha hydrogen where that methyl is, would the OH minus still favor connected with steric issues?
If there were an H here?
No, an alpha hydrogen like where the methyl is.
Oh, here?
Yes, if they're on both sides, but there's only one on one side and three on the other, if OH minus would still favor the kinetic.
No, so it would favor the thermodynamics. So yeah, I think the one exam from 2016, I actually did have the same thing without the methyl there, and it would not really give you the product that you want as the major thing. Like I sort of did the disconnect and then didn't double check that it was the only thing possible. So,
So would this still work with like NaO, ET, ETOH, and heat?
yeah, yeah. So alkoxide bases will also do the same thing as hydroxide. Oh, okay. Submit that for a regrade. Yeah. Welcome. Okay. So questions about these two? Yep. Nope, that would work too. Yep. Okay. So, any other questions about these two? Okay, cool. Okay, so this one, again, we've got two carbons with oxygens in different oxidation states. We're going to assume the lower oxidation state one got attacked, so we draw the disconnect right next to it. And that puts us at this, and if we want to have this start out one oxidation state higher than it ends, then we're going to probably make it an ester. We might as well make it the same ester that's over here just so we don't have to deal with weird transesterification issues. All right, so we could draw it like this, or you could draw it like this. For this one, you would have to use the same base as like whatever the alkoxide groups on the esters are, or again, LDA. Okay. And I deliberately modified this one to be symmetrical so that either side can attack either one and you still get the same thing. Okay. Questions about that one? Okay, cool. Alrighty, so how about number 3? I suspect a lot of people are going to raise, yeah. Okay, so there's sort of two places to start on this one. I guess the most obvious place is just draw the starting materials if you can. So methyl vinyl ketone is a ketone with a methyl group on one side and a vinyl group on the other side. And the other one is 2-methyl-1,3-cyclohexane dione. So parent chain cyclohexane. Dione means there's two ketones at carbons 1 and 3. That's a ketone, that's a ketone. If you drew this as an aromatic ring, I saw a surprisingly high number of people that did an aromatic ring and still had the double bond O's coming off. That is an octet violation though, so it's got to be cyclohexane with the double bond O's coming off, and then 2-methyl means that there. So. Okay. Alrighty, so those are your 2 starting materials. If you got those, then you're well on the way there. If not, you could sort of still figure it out. Like I saw a bunch of people who got the starting materials wrong, but because I said Robinson annulation, they were still able to figure out like a decent part of the mechanism. But let's kind of walk through that and see where it gets us. Okay, so Robinson annulation, remember one molecule does Michael addition onto the other, and then the other does aldol condensation back onto the first one. So if we want to do Michael addition, we got to be attacking on here. So we're going to start out this thing doing Michael addition on that guy. All right, so let me draw it down here. Okay, and I didn't specify a base, so if you use like hydroxide or any alkoxide or whatever, that's fine. Or if you just said base, that's also totally okay, because my bad on being vague. So I will go with hydroxide just because that's how I wrote it in the notes. Okay. Okay, so Robinson, we deprotonate in the middle. I make the enolate. And kick down, kick over. Okay, so that's the Michael addition product. From flipping through, I didn't grade this one myself, but I did see a few people that ended up with the wrong carbon count after this step, and that kind of really sets you up wrong for the rest of the problem, unfortunately. Although if you remember that Robinson makes a 6-membered ring, you may get back on track. But yeah, numbering stuff is kind of helpful for figuring out how this looks. Okay. And then again, I didn't specify a proton source, so whatever you use is probably okay. So we finish up the Michael addition by protonating. That gets us to here. All right, so we're done with the Michael addition. Now it's time for this thing to deprotonate and then go attack back on the first molecule. So let's make an enolate down here. Take the H, pick up. That. Oh. And then now it can go attack over here. So that's that. And then to finish up aldol condensation, first we got to get the O, this oxygen protonated, and then we can get it off the molecule entirely in the next couple steps. So like that. So that's the aldol addition finished up. Now I just got to do the condensation. So if you remember in base, this is going to be an E1CB mechanism. So you make the enolate first. And now we boot out the leaving group. And there, we're done. Okay, so this is the Wheelan-Mischler ketone, which turns out to be really useful for a lot of different synthesis projects, especially like steroids. Because if you guys remember the epoxidation of cholesterol lab from like the start of the semester, like a lot of steroids have this kind of structure going on. where it's like 3 6-membered rings and a 5-membered ring. This is very frequently used as like the first 2 rings of the steroid. Okay. Questions about that? Okay. Alrighty. So we got 13 minutes left. So going through all the parts of the synthesis problem number 4. Yeah, I guess like if you showed it or not, it probably doesn't matter, like, because I didn't specify conditions, so I think you shouldn't have been marked off if you did not write heat at least. So yeah. Okay, so let's go through the 3 parts of number 4, just so I can maybe pick 1 or 2, and then we can go into the mechanisms after that. Who wants to see A? Okay, how about B? Okay, how about C? Okay, I think I've got the most hands for C, so I might do that one. Yeah, and I have the key posted, and by this point in OChem, like, there's so many different ways to get stuff done that if the way you have, like, looked reasonable and worked, even if it's totally different from what I have on the key, then that's totally fine. So, okay. Okay, so C, we're going from here to here. Okay. So, I guess the first thing that you want to do is get any kind of handle on this molecule at all. Radical halogenation of alkanes is kind of the only good way to do that. So at least get a bromine on there so you have some place to start. Okay, so from here, the version that I put in the key is actually not the most efficient version. It was sort of the version that uses the reaction I was trying to build a synthesis around, but a few people actually found a better way, so good on you, that's awesome. Maybe I'll put that way up first, and then if you want like another way to do it, you can go look at the key too. Okay, so what those people did is draw the disconnect here, which pretty much means like, okay, OH on the first carbon away from the disconnect. This just looks like you turn this into a Grignard and go attack a carbonyl. So yeah, I was trying to be all fancy and being like, oh, if you make an ester over here and then we'll bring in 2 copies of an ethyl Grignard and attack twice. But you don't actually need to do that. There's a better way to do it actually. So, alright, so let's just turn this into a Grignard. I guess if I had wanted to work around that, I could have made these arms longer, and then it would have been too many pieces to bring in as 1 carbonyl from the start. But I did not do that. Okay, so pretty much all you have to do is turn that into a Grignard, and then you can just straight up bring this guy in as 1 piece, because it's not over the 6 carbon limit. And that gets you the product. Yep.
At what point would you not be able to do that? Like you said, like the arms being longer?
Yeah, so I guess like right now this is 5 carbons. If I had made them like 1 longer on each end, then I would not be able to bring this in like right from scratch. I would have to either build it myself or find a different way to make this happen, like drawing the disconnect in a different place.
Just a question, or it's like in the original way on the it's like the carboxylic acid on the side. Why can't you do like the first step as CH3Cl with AlCl3 and then KN?
Yeah, so you're, just to draw that up here. And I saw a surprising number of people try to do this actually, so it's worth addressing, but this is for electrophilic aromatic substitution, and this is not an aromatic ring. So yeah, it's gotta be aromatic if you want to use any of that stuff from the EAS chapter, unfortunately, yeah. Like, you're not the only person who did that. Like, I saw a bunch of people try EASing stuff onto a non-aromatic ring. Or in part A, I saw a bunch of people where they're trying to do stuff with this, where they ended up using similar conditions, and they're trying to add stuff like, technically it's an aromatic molecule, but they weren't trying to add it onto the aromatic ring directly. That also doesn't work. Like EAS adds directly to the ring only, unfortunately. So,
I have a question about the short mechanism. We need to worry about the grignard pulling off protons to form like an enolate, and also sterics being an issue with the attack.
Good question, because we've seen this reaction like back in chapter 19, and then we didn't come back and readdress it in the light of like what we now know about alpha protons. The answer is no. I have not seen that happen, and I think the reason why is just because it's so much more nucleophilic than like the other bases that it's going to prefer attacking for the carbonyl instead of deprotonating. You might get some alpha deprotonation, but I guess like for whatever reason the direct attack is more favored. Yeah. But yeah, that is definitely a thing that you want to check now that we know there's two different sites where things can happen. Like weighing how much one is likely to occur versus the other is always worth a check. So. Okay, other questions about that? Okay, cool. All right, so I'm going to leave A and B kind of as is if you want to check the key, or if you have questions about whether your process was equally good. All right, how about 5? I feel like not too many people had a hard time on this. It's basically the same reaction 3 times in a row, so if you got it once, you got it. All right, how about 6? Okay, yeah. Okay, so 6, there are actually a couple different good ways to make this happen. Okay, so I combine these two. Okay, so the crucial first step is even figuring out what needs to happen where. Numbering carbons. All right, so tracking oxidation states might even be the easiest way. I don't have any oxidizers or reducing agents here, so I've got 1 carbon with 2 bonds to oxygen, 1 with 1 bond to oxygen, and 1 with 3. So like figuring those out might make things easier. So I'm just going to say 1, 2, 3. So 1 has to become this one, which you could also figure out just from looking like it starts with a T-butyl group attached to it, ends with a T-butyl group, so that's got to be carbon 1. 2 is got to be here, and 3 has got to be here. You can do that either by tracking connections to like alkyl groups that don't change, or by counting connections to oxygen. All right, I might not have time to finish this whole thing, but I'll get us started a little bit. Okay, so parts that we got going on here. We got an aldehyde, an alcohol, and an acid. We haven't explicitly seen any reaction between aldehydes and acids, but we have seen stuff going on between aldehydes and alcohols. This is like hemiacetal formation. So maybe let's try making a hemiacetal first and see where that gets us. We also know that's going to have to happen because 1 and 2 end up bonded to each other through an oxygen, so that's kind of looking like what happens during a hemiacetal. Sorry, did I see a hen go? No? Okay. All right, so hemiacetal, I might get a little bit lackadaisical on showing protonation steps here, but basically we protonate the carbonyl. And then this OH can come in. Get to here, and then if you deprotonate, I'm actually going to redraw this a little bit differently. So that's where that gets us. So we've made the bond from carbon 1 here to the oxygen to carbon 2. Now we need to close the ring down. We need to make a bond from this carbon over to here. So we have now an alcohol, we have a carboxylic acid. This is looking kind of like Fischer esterification. Okay, so I think I'm going to have to cut it off before I go through the whole Fischer mechanism, but that's pretty much what you want to be thinking of there.
Really quick question.